All right. Um, number sixth time we've met together, and now we're delving into the runtime proper. We started looking at that a little bit last time with the boot sequence and how Dawn verifies your keys, and main actually instruments your keying process. Then there's going to be like the surf worker process and some other things that we'll have to consider and put together. But to talk about Vere, which is what we're doing, you're going to need to be at least comfortable reading C. And then I think for the homework, we're going to give you one that's fairly scaffolded. It's going to be kind of like the JET tutorial from before, but have you actually just work with U3, work with nouns, because U3 is ref counted and have some other quirks to it. Aries is not written using the U3 noun library. It's implementing its own noun library. So it has a completely different feel to how you're doing things inside of it. All right, let me switch over to my regular presentation mode, and we will go forth. All right. So, right, ultimately the point of Arvo, the inner vision of all of this is that we're running this. I can write it with the second part explicitly wrapped up there, but like ultimately, right, this is our life cycle function. This is our frozen life cycle function. This is the thing that makes sense in terms of knock to just evaluate the next event. And I think we understand that pretty well at this point. We've seen it in a lot of different forms and encountered it in different places, but on any real system, we need a lot of scaffolding. Real computers have memory, they have chipset architectures, they have multi-level memory, they have operating system conventions, they have event process spaghetti, they have ROM bootstrap sequences. And so conventionally, when we've talked about an operating system, we've meant something that takes explicit care of things like memory paging and scaffolding and evaluating code and handling multi-threading and multitasking and these sorts of related processes. This is one of the reasons that calling Urbit an operating system can be somewhat controversial depending on where you're looking at. I think ultimately we would like to see the runtime push down farther and take care of more of this. The vision of running a bare metal knock VM, Arvo handler is a nice one. We're a long way from it because we're still sort of chiseling out of the rock, like what is this actual diamond form of the Arvo kernel and everything else look like. But in any case, so we have this runtime interpreter, and this is what allows us to treat Urbit as at least a platform, if not yet a full operating system in the conventional sense of managing everything on the machine. There have been various Urbit runtimes over the years. Vere is the most venerable of these, and it's the one we're still using. Its name is a reference to Edward de Vere, who's one of the who's Curtis's favorite hypothesis for the actual authorship of the Shakespeare plays. So a nice subtle nod there. For what it's worth, I am a Stratfordian and think that there actually was someone named William Shakespeare who wrote what he wrote. But Shakespeare's a lot to type every time you want to talk about the runtime. And there's Aries. There has also been Jacques and King Haskell. King Haskell was a keying process written in Haskell that proved to be a lot to maintain for various reasons of code style and architecture, and was dropped a couple of years ago. And Jacques was an attempt to write it on the Java virtual machine. So that we would actually have a JVM runtime. And so I think there's some interesting research. It was an interesting research effort, and I think some of the good ideas from that did make their way back into Vere, but it's no longer an active project. So Vere is our standard runtime. It's written in C, essentially entirely in C. And then Aries is written in Rust, which allows us to have foreign function interface calls to C and so forth. Aries was kind of started as a research project to solve some deep theoretical challenges around producing NOC efficiently on a contemporary chipset. Right now, core development for Vere is almost entirely Urbit Foundation and Twan. And Aries is a joint product of Zorp, Twan, and Urbit Foundation. So there's several players in both of those. We're going to take Vere as our normative runtime. We could talk about other things with Aries, but as I've been working on Aries, I found that it's very much in flux, and it's sort of hard to actually nail it down to, what is the architecture of Aries going to look like in some sense is a harder question to answer. Also, I think that Rust is probably less familiar to the modal programmer coming in and looking at the code. I certainly found it kind of an interesting adjustment. Okay, so we mentioned last time there's a boot sequence. The runtime spawns a king, and the king spawns a serf, and these both run for the lifetime of the Urbit process. So right now there's two competing frames for thinking about how to structure the Urbit process. So there's king serf, and then there's earth Mars. All right, so king serf basically says the king takes over the IO and event log material, and the serf is in charge of Arvo and NOC handling. The Earth Mars frame is designed, ultimately the hope of Earth Mars is that it can move event log truncation online. So you'll be able to do event log management without having to power down your ship. And so then the only reason you'd have to power down a ship would be to actually change out the runtime. And so this would basically this would move the event log into Surf and then name it Mars, and so then you'd get truncation eventually is the main thing. Basically, it's moving functionality out of the king into the Surf, and then you get this. This is actually a mostly complete PR since February of 2023. There's a bug that has prevented it from being merged, and depending on what happens with Aries, which is a Surf process, it's not clear whether or not we'll actually end up going down the Earth Mars road, or because with Aries, it would actually require more work on Aries to make Aries a Mars instead of a Surf. So something that's coming down the pike of discussion to be aware of. All right, so we're going to talk about Vere. Vere is its own repo, the Urbit Vere repository. The code is inside of the package directory here, and there's 6 top-level folders here: C3, ent, noun, urcrypt, and Vere. Of these, the simpler ones, ent provides entropy for the runtime. All right, so now for a minute, what is entropy? I guess let me do we have C3, ent, noun, urcrypt, and Vere. All right. So ent and are the smallest ones, so I'll address them first. All right. So what is entropy, right? So we have this problem on a computer of how do we generate a pseudo-random number, right? Like how do we do something that appears to be random? And so there's interesting games you can play with, like what that might look like, right? So if I start typing the sequence of numbers, can anyone tell me what the next number in the sequence is going to be? It is deterministic. And if I change it a little bit, you might figure out what it is.
I don't know enough of pi. I'm sorry.
Okay, well, you recognize it though, right? Five is the next one, and then I don't really know past that point. But right, so it's a decimal expansion of pi. And so this is a deterministic sequence that actually has some nice properties. As far as we can tell, the numbers are equally likely to come up. They're uniformly distributed. But it is deterministic in that we can write an algorithm which would tell us what the next value is. And if you didn't know the sequence ahead of time, then you could treat this as an unknown quantity. Computer pseudorandom numbers are subject to all sorts of concerns about, are they cryptographically secure? Is there like a salt or an additional value that's manually added in that alters the outcome in a deterministic but less predictable way? Are the values that I'm getting out of this pseudorandom number generator actually uniformly distributed? Are they normally distributed? Or do they have a bias in some sense? And so in cryptography and in physical simulation, these become immensely important questions, because you don't want, in a game, it's not that big of a deal if you're not quite correct. But if you're doing a Monte Carlo simulation in physics, or if you're doing cryptography, this becomes enormously important that you're actually doing this correctly. The solution on Unix systems today is to use a process called dev-urandom. And so this is what system entropy is actually feeding from in Urbit. Dev-urandom feeds a number of unpredictable hardware sources, such as network latency and user keystroke latency, into what's called a cryptographically secure pseudorandom number generator. And then you get a value out of that you can basically consider valid for processes that you actually need to know that there's no predictable way of doing this. Actually, Native Planet, just in their manifesto, they were pointing out that your ALU is a weapon. And for a long time, there was this problem of export controlled cryptography. This is up into the aughts. 80s, 90s aughts of you could write an algorithm, but you were not allowed to put it in code that would be distributed outside the country, for instance. And this was a huge issue. There's still some weird legacies. When I was in grad school around 2010, I got a copy of the Monte Carlo nuclear MCNP, which is the Monte Carlo nuclear program. It doesn't stand exactly for that, but it's a
Wait, really? I use that same program.
Yeah, and it's pieces of MCNP
Yeah.
go back to the 1950s.
Yes.
It's possibly the oldest piece of software that has been in use. But did you have to sign the agreement, the export control agreement?
Oh, I had to get Sinwitty.
Yeah.
Yeah, so I had to do a step further than that. Yeah, it was a pain.
Yeah. And that's because it's also used for nuclear simulation, but you had to do this with cryptography. Cryptography was considered a munition until just sort of de facto there was no way to contain it anymore. Anyway, the long story short is that ent is your tooling for retrieving entropy from dev-urandom on your Unix device. And it's one of the reasons that you can use Urbit for cryptographically secure calculations, modulo the runtime in Arvo have not been hardened against attack. So, all right, and then the other really small one is and this has to do with bitstream serialization, and it's just I don't really know why these two are separate from everything else, but they're just pieces of the system that didn't. I think they kind of feel more like standalone libraries rather than integral parts of something else that's going on. So, there they are. Those are two single-purpose libraries. All right, C3. C3 is an interesting one. This is essentially types and definitions for C3, which is the set of conventions that Urbit adopts. Defs is most of the interesting material here. And so if you look in here, Urbit adopts some conventions, of course, that are different from conventional C. C3 doesn't do anything that is Urbit specific. It is Nox specific in that, we're defining a yes and a no that are a 0 and a 1. We're defining a cab and a double cab that flip the polarity of logic so we can go one way or the other. There's a C3 and a C3 or. There's a lot of type definitions. So in C, if you say that you have an int, for instance, you actually don't know what kind of thing this is on the platform. It depends on the word size of the platform that you're running on. And this is a mess. And writing out, uint 16 cab t as your type every time you want to talk about your type is a little bit cumbersome and potentially error prone. And so the solution for Urbit and for the C3 C discipline is to rename everything as standard type. So there's a C3 double, there's a C3 word, there's a C3. I don't know why S is listed as single here, but anyway, you get these. It's also interesting in that it flips the polarity of C in a very rational way, which is that unsigned integers are in a sense more fundamental to a computer than signed integers, and yet C privileges int over uint in terms of terseness of representation here. So now we have C3 word and C3 word signed as our values here. As with ARA bit width markers, if you've run into these before, this documents programmer intent, but it doesn't generally enforce it. C will let you do crazy things with types because it doesn't care. It's not actually going to enforce typing very hard for you. And so you're, sure, right over the end of your pointer array, whatever, it doesn't care. So most of C3 is actually a set of conventions that are just directly on top of C99. The other interesting thing are the moats. And the moats are these wrappers that let you match terms from, if you unpack a term from a noun, as we'll see how to do later on, then it matches to one of these values here. And so this just gives you a quick definition to refer to that value anywhere that you run into it. So yeah, they're in there. Since they're I'm going to say pound define because I don't like saying hacks define. That just sounds weird to me. Pound define, then they're there. All right. So much for so much for C3. Not a lot else to say. It's a discipline. We're going to run into it a lot, but it's there. All right, Urcrypt is the next most complicated one. These are crypto libraries. The point of Urcrypt is that the C crypto universe is kind of complicated and it has a lot of different libraries that are pulled in to make this possible. And there's various versions of AES. There's various SHA algorithms out there, and they all have different interfaces. The point of all of the Urcrypt tooling is to provide a uniform interface so that ultimately, when you're over in, if you go look at the Shax jet, somewhere there's a I guess it's probably a U3 noun. It's going to be named something like this, U3QE Shax. And so this will operate on a noun. It'll take a noun or however many times or whatever. But thanks Copilot. It's probably just copying it somewhere. But ultimately, what this is going to boil down to is there's just going to be a call that's something like this, and that's the value that gets returned. Urcrypt is just a wrapper for all of these. I like how it's just trying to guess what I'm actually saying here. What am I working in? I'm working in Markdown, and it's fine. Anyway, so Urcrypt is really nice. And I am particularly running into this as Mastar Botek and I are starting to work on the crypto jets in Aries, because we can just wrap Urcrypt and make the direct same calls, and we know everything is going to behave the same way, and it's not a slightly different implementation or whatever. But Urcrypt is probably going to be moved into its own repo very soon. And then it won't be something that you have to explicitly look at here. It's just an extra piece you have to
I
call
think
out.
it is already.
Well, there
It's
is
just-
a repo. I
There's a
don't know that it
repo,
has,
yeah.
I don't know that it's been removed from Vere yet.
Okay.
Yeah, Matt built it as a standalone because that's the only way to efficiently keep this maintained with Aries. I mean, there are good architectural reasons not to have cross repo dependencies, but man, sometimes you just want a cross repo dependency for this sort of thing. I guess you can set that up with Git hooks if you really want to. All right, so then that leaves the other two, which are noun and var. Today, we're going to spend most of our time in noun and then a little bit of time in var talking about the runtime architecture itself. Noun is the gorilla of Urbit. This is where the runtime is doing. This is the library that makes it possible to do everything that is done in Urbit. So this is the U3 library system that manages everything, and then this is actual runtime architecture. All right. Let's take a quick look at Vere before we get into noun, just so you can see the kind of the structure here. And I think I have, yeah, I do. There we go. All right. So there's a lot of C files in here and a few headers. Some of these are like aims tests and so forth that may get called on a build or if you explicitly run a set of tests, but otherwise they don't matter. They're not really significant. We started to look at these last time when we looked at main.c, which is your int main, right? It's your main entry point for what's going on. Some of the others, auto, are your input output drivers. They're handling what's actually going on with your Unix system calls. Dawn is your key validation. We looked at that a little bit last time. It either has to contact Azimuth, or it has to make sure that it has a valid key for a commit, or it gets skipped if you're doing a fake ship boot. Disk is your LMDB event log management. Foil, it's labeled file syncing. As I was going through it, it seems to be kind of a grab bag of file stuff that doesn't seem to fit anywhere else for some reason. King's your king. Lord is your IPC management, your interprocess communication between the king and the serf. Mars is right now, it's mainly event log stuff because of the Mars Earth split. And so all of the event log replay that has been set up recently, and I believe the epoch system stuff is all instrumented in Mars. Not actually sure if the epoch system is in there. Hey, there's Matt. He showed up just now. Matt, you showed up at the perfect time. I have a question for you. Are you ready?
All right.
Is the epoch system stuff in Mars.c?
No.
Okay,
Disk.
where's it's in disk? Okay. I guess that's the other place it could make sense. Mars is your event log stuff anyway, replay stuff.
Yeah. Yep.
Yeah.
Synchronous replay.
Yeah. Newt is is a noun library. It's a noun handler. Peer is more file system stuff. Say Surf we'll take a look at later today. Time wraps all of your Unix Urbit time operations. So you have to do a lot of conversions between, are you working on the Unix epoch or the Urbit epoch, which are of course vastly different sets of operations. Those are handlers for those. And then Ward is lifecycle management around things to make sure that you start things up and shut things down correctly. There's a sense in which Vere is kind of complicated, but it's also not super interesting in a way, because it really is just scaffolding for, can I set up an Arvo noun, and then noun, which is U3, is actually doing all of the work. And so I think noun is your most interesting part of your Urbit runtime, in a sense, that you're not just scaffolding something else. All right. All right, we have a number of these in here, but first off, we need to talk about nouns. So in the docs, it kind of refers to this as lib noun, but this is package noun. It's just the contents there. All right. All right. So going back to our beginning Urbit materials, right? A noun is either an atom or a cell. If we have to decide how to implement a noun in a language like C that prefers arrays and pointers, right? Like C doesn't naturally speak trees and pairs and so forth. So U3 is Urbit in a sense. It's all the Urbit specific. It's the memory operations. It's the tracing. It's the profiling tools. It's the support for allocating, deallocating, manipulating, extracting, injecting nouns. All these things. A noun is actually, if you go look up wherever the noun typed F or whatever is, it's a C3W. So going back to what we saw a moment ago, this is a C type. It's not signed, right? There's no S suffix on it. And it's a word size for the old standard Vere machine. So we can infer that it's a uint32T as our type there. And this means that every noun in Urbit at its root is represented as a 32-bit integer. So this gives us an interesting problem, because what does it actually mean to have a 32-bit integer of these values? Right? Like we can clearly represent things that are larger. We can represent things that are smaller. How are we going to do this in a consistent way? So what we do is we're going to 12, 16, 20, 24, 28, 32. All right, there's a 32-bit integer. We are going to take a bit mask on the first two, the most significant bits, to specify what kind of value the noun is and thus how to approach it. The easy case is if your leading bit is 0, then you have a direct atom. And this is what's called a cat in the system. There's a lot of cute little things that you'll run into if you start getting into Vere. They aren't that bad, but they're a little weird. You have to get used to them. I guess this harkens back to the acid trip nature of early knock and so forth. So a direct atom is a cat. A direct atom means that we are directly storing a value that is 31 bits or smaller in what we have here. So if you're representing, 0x1 or I guess you could fit a 4-character ASCII atom in this, as long as it doesn't hit that top byte. All of these are going to be valid direct atoms. The other case is if it's a 1, 0, then it is an indirect atom, which is a well, let me break this up differently. If it's a 1 cab, so 1 and then whatever, it's an indirect noun, which is a dog. You do have to check these. The only way that you actually have to worry about it is there's a couple of helper functions that are like U3 is cat. It's a pound def or something that you run into. Other than that, you actually don't have to remember these. You just have to remember that you are working with a direct or an indirect atom. If it is a 1, 0, then it's an indirect atom, which is a pug, or an indirect cell, which is a palm. All right, so all cells are indirect. Right? We don't have any direct cells in this sense. Okay. When you have one of these, what you actually have is the first 2 bits are reserved, which means that bits 29 through 0 are a word pointer into the loom. All right. This is the real reason that Urbit was originally limited to 2 gigabytes in the loom. The loom is our memory arena. We're going to talk more about it next time and see what's going on, but it's our memory arena. So this was the origin of the 2 gigabyte limit. And until you had like ways of paging or redirecting pointers or so forth, you didn't have a way of referring to anything that fit outside of this 2 to the 30 range here. All right. There's also one reserved noun, and this is U3 none. All right. This is your not a noun. You know, we have something similar in floating point operations, for instance, not a number. U3 none is not a noun. It often means that there's a failure for some reason, something's gone wrong in an attempted calculation or so forth. The most common place I run into it is, let's say you have a jet that only jets certain cases. So like Scott is like this, right? So you remember, Scott send P value is used to write a value to a string, or I always forget which way it goes, but I think that's the way it goes. Or maybe it parses it out of a string. I always forget and have to do it manually. It writes to a string because Scott's the one you use when you're writing a scribe path. So Scott writes to a string. But if you go look at the jet, you can do this for any noun. You can do it for a UJ or a UI or a P or a DR or a T or whatever. I don't know why you do it for T, but you can do it for any of these. You can Scott for any of these. However, most of these are so uncommon that the judgment was made that we're just actually not going to implement them as a jet. So what the jet does is it receives the noun, the value that you're trying to process. It checks the type that you're trying to go to, and if it's send P, send DA, send DR, I think there's one or two others that it hits, maybe like UV, UW, I think. Then it does it in the jet. Otherwise, it returns U3 none. And U3 none coming back from a jet means this jet failed to process, go run the hoon instead. So we can actually fall through a jet back to hoon and then evaluate the hoon on receiving a U3 none in Vere. Okay. All right, so let's look at a simple file and just get a feel for sort of what these behave like. All right. So this is add.c. This is a jet. And a very common pattern, we're just going to look at this first one, which is U3QA add. We're going to look at all of them in a minute, but we'll start with this one. A very common pattern is you have to extract the values from noun into some sort of C-typed value, carry out your manipulation, and then wrap them back into the noun. And since what you're getting may be a direct or an indirect value, and it may be a big num, right? It could be a big int or a big num. You actually have to deal with these cases explicitly. So this jet receives 2 atoms. We're not going to worry yet about how it receives these atoms. It receives 2 atoms, and it says if I have a cat and a cat, if I have 2 direct atoms, then I can do a naive C-style addition of these 2 values and then return whatever it means to imprison that value. Now, if we're thinking about bit width, we actually have an interesting case here, right? Because we could be adding 2 values that are 31 bits wide, which means they'll overflow into something that is not a direct atom anymore. Right, so when I do that operation, I end up with something that is now an indirect atom. So I can't just return C directly as an atom, even though that would be a valid, like as a C3W, that would be a valid direct atom. Instead, I have to run it through a wrapper to put it back into a noun. So it's telling me I'm passing it a length 1, one atom, like one value that's going into the noun. and then I'm writing into the noun, and then I'm returning it. It is returning this value back to me, even though it's accepting it by reference, and it's returning this value back to me. So this is going to be your pattern. All right, go ahead.
Wouldn't that even overflow before, like, wouldn't that overflow on line 14? If A is 4 billion and B is 4 billion, how can you put that in C, which is also just a 32-bit?
But see, if it's a cat, you know that the 0 is empty. Your most significant byte is empty if it's a direct atom. So you actually can't get 4 billion. You can only get 2 billion.
Okay, that makes sense. That's
your safety margin.
Okay, cool.
So yeah. And there's some interesting games you can play with this if you actually know things about the bit width with left shifts and right shifts and so forth. Like regular C, right? Like regular C, if you're going to divide by 2, just right shift. Don't bother with a div operation. All right. Anyway, so you're gonna unpack. You're gonna do checks, and it's faster. So you're gonna unpack. You're gonna do checks. You're gonna do your operations in C, and then you're gonna wrap back up into a noun. This is your process. In the other case, what does this look like? All right. In the case that you have an indirect atom, you have to define this MPZT. Like, okay, what is this? So because you might be getting a big num out of these values, we're going to use the GNU multi-precision library, GMP. So these are multi-precision values. We are unwrapping them. If we go look at what the R library here is retrieve. So we'll come back to that architecture in a minute. We're retrieving the value A into the local value AMP, which is an MPZT, because we're doing an MP and multi-precision unwrap. Do that for A and B. Add the values together, and then we're going to return A. So there's a reference to A needs to exist, but we actually need to clear B explicitly. So one of the painful parts of working with U3 is that C doesn't give you reference counting tools. So reference counting is a way of tracking the number of pointers to an object in memory so that you don't have a memory leak. It's a way of it's like poor man's garbage collection, so that you can free memory at the appropriate time, not too soon, not too late. As long as there's a reference to a value, you don't want to free that value because some function somewhere may rely on it. U3K gains a ref count. Okay, actually what's happening here, I missed this middle case, which is if A is 0, then just return B. Right? If I'm adding two values together, if one of them 0, just return B. I don't know why it doesn't do this. I guess it doesn't do this for B because we're short-circuiting on the A logic in line 13. That's what's going. Okay. We're gaining a reference to B, and then we're passing it back. We're saying don't get rid of B. Like, be aware that B needs to continue to exist. In cases here where I've allocated multi-precision values on the loom, I have to explicitly clear the one that I no longer need. And then since I'm returning the other one, that reference count to it can persist. This is a little weird and painful if you haven't done this manually in a language before. The other weird thing is that there's also two different protocols for reference counting used by different parts of the system. So we are going to run into transfer semantics and retain semantics. All right. So transfer semantics means whenever you send a value, you relinquish a ref count. All right. These are, yeah. So these are things like U3Q. No, U3Q is a retain. U3K is a transfer. We'll look at that in a minute. U3K. All right, and this one. So when a retain semantic means if you send the value, you keep a ref count. A little bit confusing until we start looking at examples here. So here we have a version of add, which is a I want to make sure I'm saying this correct. I run into this all the time. I want to make sure I'm saying this correct. U3K is a transfer semantics. Yes. So I'm sending the values over, but then when I get the values back, I have to explicitly free the values. When I have retained semantics, I clear the things that I no longer need or decrement their ref count, and then I send the things back because I'm having that come back around. All right, we'll go back through this. We're gonna see this more than once. That's your first intro to the fact that there's two sets of conventions, and it's kind of confusing. It's not a total mess, and most of the time, you look at the other functions in the file where you're working, and you follow the convention those files are following, in terms of what you have to keep track of, what you don't. All right, so we'll start there. We'll come back to this as we come back around to working with these.
Neil, just a quick question here.
Yep.
Is this trying to like think about this in terms of like C++ style is like or C++ 11? Sorry, are you familiar with like move semantics and that sort of stuff?
I'm not familiar with 11. My C++ days were earlier than that.
Okay. Okay. So just maybe to try and explain this a little bit more abstractly. Then it's like sort of is it basically just like one of them like relinquishes it and says like this is yours to handle now, and the other one says like I'll give you this, but I'm also going to keep one of my own. Is that kind of like the difference between these two types of
yes
transfers?
Transfer relinquishes a ref count. It means if you
So
send it somewhere
I'm just
else,
giving this to you.
Right.
Like this is now yours to handle. Like you will deal with if it like garbage collected or well I guess ref or decrementing the ref count, that's yours to handle with now. So I'm not going to decrement it, I'm just going to leave that to you.
Yes.
Okay.
I send it to you, it's your problem.
Okay.
Retain means I'm in charge of this. I send it to you, you use it, but I still have to deallocate it.
I see. Okay.
In C terms, this is sort of like new delete stuff, except with new delete, you just have one ref count, right? Like, and then you delete it. So it's not quite the same. This is one of the big things that Objective-C introduced and why Apple liked it was it automatically handled ref counting.
Yeah, there are some like facilities in modern C that do this sort of stuff. They're like there's like move semantics and like doing like you can either pass the ref or like pass this thing as reference or pass it as there are different words for it. I don't remember, but they have similar concepts to this. That's great. But okay, that's helpful. Thank you.
Yeah. Anyway, so it's a thing you'll have to get used to working with, pushing around. All right. So U3 is sort of also still not Urbit. Okay. It's a noun library, and it actually doesn't know about things like Arvo and so forth. But it does make some guarantees, or we need to make some guarantees with Urbit within and without. One of the guarantees that we make outside of U3 is that we log every event before it goes into U3. And this means that if an event crashes, then we can like pop it off our stack and throw it away, whatever we need to do. But like Vere keeps track of the event before it goes into U3. It's in the log, so it knows how to handle it. U3 will maintain, it'll maintain a single reference. I guess I should say ref count to something that's told is permanent state. So you can have this idea of permanent state that you're actually, as long as you are correctly ref counting, you will not accidentally free. It's solid state in the sense that we were talking about earlier, which is that you can abort an event without damaging state ultimately, and then you can snapshot permanent state and prune logs and everything and read forward from a particular instance. Now, those aren't unusual to you because those are the same guarantees that Urbit is making, but now we're making them in the runtime in an analogous way so we can do this. The event log and the memory stuff, we're going to get into next week when we discuss the loom and the road model and we get more into the king. Today, we're really going to be talking about nouns and Vere, in particular, the serve. All right, so we'll come back to add in a minute, but for now we're going to look at noun. All right, so what do we have in noun? So noun's kind of a long set of libraries here. All right, so we have allocate, which is our memory allocation functions. These get used throughout, but they're kind of we're going to discuss it a bit more when we talk about the king. There's a lot of reference counting features that you run into when you're writing jets. Like we saw U3Z, which loses a ref count. That is actually a shorthand for U3A lose. The other weird thing about this is this was written enough times by enough people. It's probably defined in the header file. Let's see, U3Z. Yeah. U3Z is U3A lose, just right after the function prototype there. It's been used enough by enough people that there are shorthands for some of these, which can be kind of confusing, especially because the shorthands don't follow the prefix convention. So there's a U3Z Zave, which has to do with cache memoization, but U3Z is to lose a noun, it's to delete a noun, it has nothing to do with Zave. So there's some quirks. They're not so bad. It's kind of like learning Hoon in that you just get used to whatever these weird preferences are. Events.c is loom management and snapshot management. So it's just kind of taking care of building those actual components here. So we'll see that one more next time. Hash table stuff is building fast custom hashing for the runtime. So, similar to the way that Arvo maintains the worm cache, so it gets fast lookup of things. The runtime does some hash table lookups and should do more. So we'll probably see that increase in utilization in the runtime soon. Imprison is an important one. Has an odd name for it. This is the way that you take a C3 type and put it into a noun. So when I was looking at add, it had a U3I. I think word is the one that I ended up using. I must have used words with a single value, which is the same thing as this. But what this is doing is this is accepting a 32-bit wide value and doing its check. Can I wrap this directly as a U3 atom, or do I have to allocate something and make these conversions and everything, and then pass this back out? Obviously this is doing a lot more. So U3T is tracing, so it turns on tracing, turns off tracing when it's done in case things are breaking and we're having a memory leak or something like that. But it has to do word. This is a word allocation. U3A is our allocate, so this is a word allocation, and then it's writing these values in, and then it's setting things inside of the struct that's part of the U3 noun. I guess I told you a little bit of a simplification earlier. Part of those, maybe those are in types. U3 noun might actually be in C3. Let me see if I can find that really quick. Well, let me just find this. I told you a U3 noun was a 32-bit word. That is not quite true. There's some like type union stuff and struct stuff that goes on with it too. And I'm trying to see where this is actually declared the first time, which I don't know offhand where that's going to be. Well, I know where this is in the docs, and I can find it very quickly, but I should show you what the whole structure looks like. Let's see, this is Vere.
We can't see anything. If
I know, I'm
Okay.
gonna copy it over for you.
Gotcha.
Um,
What are you looking for? I missed it. I'm sorry.
I'm getting what a U3 noun handler
Gotcha.
is. Anyway, what you end up with is so a U3 noun is a word. Like I said, it's a C3W. But when you get a pointer into the loom, then it's pointing to structs that have this information inside of them for an atom and a cell. This just became important because when I was looking at imprison, it sets some of these values. All right, so when you get the pointer into the loom, so a U3A atom is an indirect atom in your loom. You're defining a mug, a length, a buffer, and mug, length, buffer. The length is if you have a big num, right? How many spots is this allocated? Is this occupying in the buffer? Yeah, it means a 32-bit atom takes up 3 times the size of a 31-bit atom. Yes, it's true. There's some interesting quirks on this. Oh, interesting. So yeah, so Moffel says this is why the insistence on 4-letter words. Yeah, I didn't actually catch that.
Yeah, that's why terms and stuff in the kernel is always 4 letters, because
that's a direct consequence.
Yes. Yep.
Eke out that tiny bit of performance.
I mean, we can use every bit of it.
Right. Although, it's not like we've actually pushed things. So with 64-bit Aries, we should switch to 8-letter words for everything.
No, because we're still supporting Vere, so no luck.
Mug is an interesting one. Mug is a hash. It's kind of a weird little field. So like if there's a copy being taken place, you can actually use this to store temporary information on the loom in a pre-allocated bit, and then you recalculate the hash after you're done. But this has to do with the hash table lookup stuff. And then the struct is you get another noun, which may be something in the loom, but may not be. This is also where you start to see the bifurcation between array-based computing, which is what chips actually do, and tree-based computing, which is sort of saying, I don't know where this noun is. I don't know what this noun is. This could be the next 2 contiguous slots in memory, the next 2 words in memory, or they could be somewhere else. Like I don't have a way naively in U3 to do any sort of efficient caching out of this. So that gets you back into subject knowledge analysis and everything that's going on with that. Anyway, imprison. Yeah, so with imprison, what this is doing is it's allocating the memory, making your pointer and everything, setting your mug to 0, because we're writing a single word, we set our length to 1, right to our buffer, and then do whatever declaration or everything we need to do. This might be writing the mug here when you do this U3A to pug stuff. But anyway, this is how it works. This is what U3I does for you. Word, chub is your double. That's your 64-bit one. Bytes is your byte. Bytes 1. Words plural, chubs plural. Those are the main ones that I ever see used. And then yeah, if you're ever writing big num stuff with GMP, then you have to use those. There's a few others. I guess there's a fast increment for you, but I don't see those used nearly as often. The words are basically your malloc, right? You're actually putting this on the loop. You're declaring this thing. Jets is your jet dashboard support. It does not actually explicitly build your jets, but it sets up your jet dashboard and handles that kind of junk. There's some logging and tracing stuff. we don't really have a lot to say, but you can turn these on, or you can pipe these to different places, depending on what you're trying to do. M is your system manager. This is what is handling booting U3, making appear. I'm in the wrong spot. No, I'm in the right spot. I'm in the right spot. Yeah. But it's doing it from the U3 side. It's setting the stuff up on the U3 side. Thank you. Manage the main thing that you're going to run into and manage is bail, which is your crash. You've all seen bail crashes. So this is your actual, you've reached an exception, something's gone wrong. Whenever you get an allocation outside of memory, these things are coming through in bail. So this is your universal exit code handler. Yeah, this is an interesting one because this is on the roadmap. I noticed when I was looking around for this. Right now, the runtime just crashes. It actually doesn't use the event codes to tell you anything about what's gone wrong. Classically, C returns 0 on success and it returns something not 0 on failure, which is again why people getting upset about knock using 0 as true is absurd. But we don't actually use error codes for anything else. We just crash. We could do more with that and maybe enable some things. Yeah, we should. Knock is a really important one. This is your actual knock executor. So this is your knock bytecode. We're gonna come back to this and work with these. And yeah, we'll do that. Options handle globally set options. There's some weird globals that get passed around everywhere. There's this structure here. There's a lot of values that get set there. Yeah, this is what I'm looking for here. So these are how the flags get set for, do you have tracing on? Are you running everything with verbose errors? Command line flags set a lot of these, for instance. Are we on a replay? Are we on a dry run replay? These are set as the globals in this U3O global struct and then extracted whenever you actually need them. Globals are kind of a mixed bag, but it's not obvious to me how else you would solve the problem in any modestly complex system like what we have here. All right, retrieve does the opposite of imprison. U3R is how we unwrap a value, extract it back into a C type. Extract is the other one. So there's an extract down here, U3X and U3R. U3X and U3R are equivalent, except that U3X crashes on failure. U3R returns a U3 weak on failure. So U3R is an attempt to do something that won't crash your runtime or whatever's going on. It ends up wrapping a lot of U3X stuff, but it does, it has sanity checks and assertions and other things, so it doesn't just break. U3R, let's see what it does with like the MP. Yeah, so this tries to do some fancy things with unwrapping the values once you have them as your atom and everything. Yeah, normally you're just pulling these out as a block of bytes or words or chubs or which are doubles or whatever you get. Same kind of operations. Met is used frequently, so this is your met, right? This is your width in bits of whatever size, and then you have to scale it to whatever you need. All right. More noun serialization. This is your jam and queue is basically implemented here. Tracing for not breaking things. Earth this is where deduplication and memory mapping lives right now. Vortex is Vere operations. We're going to come back and look at this because the way that it handles like wish, poke, peek, and everything is really interesting. And then extract is retrieve with crash, and Zave is sigless rune memoization. So nothing special there. Basically, there's two broad categories of functions that you're going to run into here. There's either single-use functions, like starting a peer or whatever, and utility functions like jam, queue, or increment your ref count, decrement your ref count, all this kind of thing. So, you get used to one, you have to hunt for the other. All right, let's see. Let's look at. All right, so the surf process means you have your NOC virtual machine, your bytecode interpreter, your jet dashboard, and some allocation stuff, like snapshotting can be there. Okay, so one of the things you want to do from your surf is you're running your NOC virtual machine, so you have to be able to track your current state of Arvo as a noun and poke it with nouns. So surf.c, let's see, it has a number of U3V calls like U3V poke. So if the surf gets told to poke something with a noun, what it ends up passing it through is U3V poke. In this case, U3M soft means, when you crash, you don't do a hard crash, you do a soft crash. That's what that's managing there. It's probably, there's a peak. Surprised the wish doesn't come through here. I would have thought the wish must just, actually, I'm not sure where the wish is going to come through. Might be worth looking into in a minute there. So the surf has functions that do these calls based on whatever they need to do, but they're calling into Vortex. So the interesting stuff is in Vortex. So first, let's look at U3V peak. All right. So we know what Arvo is shaped like, and we know that there's certain addresses that are allocated inside of Arvo. So what I'm actually going to do here is I'm going to define this peak allocation on this value. This rock is like our current state, like this is our global Vere Arvo state. And then we're going to slam the function that we just built, which is our peak function, on our sample. All right, so think about like what's actually happening here. Let me close this so we have a little more room. We are constructing a peak function against the current subject, which is in U3A. And we're doing memory management, whatever. And then we're getting the NOC equivalent of that. And then in U3N is all our NOC stuff. And then we're going to slam that function, that peak function, on our sample. Right? Like this is kind of an interesting way of querying what's going on here. So, if we go look at wherever, find where this is defined here. Oh, what do we have? What are these numbers? You know these numbers. You've seen these numbers.
Is the Vere like ARM axes or whatever those things are called?
Those are the hard-coded Vere ARM axes. So we are just constructing in Vortex, in Vere, we're constructing the NOC of a peak and then evaluating it using the NOC runtime. Kind of an interesting way of actually handling this problem. So when we talk about the Arvo-shaped noun, this is where we actually hit the Arvo-shaped noun, right? We've done all this work on Arvo side to set this up. Now Vortex is where we're actually using it. This is why you need an Arvo-shaped noun, because you know how to do things at certain axes. So ultimately, an Arvo-shaped noun only means something that defines these functions at these addresses, at these axes. And the rest of it, you could do whatever you wanted. And they could have whatever behavior you want as long as it's consistent with, to some extent, with what you expect to see. All right, so peek does it that way. Poke is a little more complicated. Let's go to, no, poke's doing the same thing. Oh, I'm thinking of poke sure. I'm thinking of poke sure. All right, so poke raw is all right. So what poke is doing is it's giving you an ovum, which is like a raw event. So we're going to use this when we're doing something like an event playback. When I want to inject a new event, like something's coming from Arvo and I need to evaluate it and return the value and make sure that it gets written to my event log and everything, I'm actually using poke sure. So poke sure does more things. It creates a noun using poke raw, and then it sets up some values around error handling and so forth, so you can actually, pop this back off the stack, so you can proceed versus persisting the state, writing this into. Anytime you see U3A, that's your global Arvo state. So you can write this into your global Arvo state that you've had this thing, and then you increment your event count, and then you release the details of that and decrement the ref count to those details, and then return success. All right, so this is your actual parser forward for your event handler in the runtime. All right, wish. I want actual wish, not wish n. All right. All right, so what does wish do? All right, it gets the text of the wish as string. Then it basically evaluates this text against your Arvo state. And then if that fails, wait, why is that U3 none instead of C3Y? Seems like C3Y should be like what we're getting back from that. Okay, well, let's do a little bit of searching. This is in K. Oh, because it's a map lookup. So if it fails to find it, okay, that's why, because that's a cache wrapper for that operation. We're checking whether or not the result of that wish is already in our runtime cache. Oh, very nice. Okay. So we're checking whether or not the runtime wish, the wish is in our runtime cache. And if it's not, then we get U3 none, in which case we evaluate in the knock what this text is, and produce those values there. Okay, that's kind of neat. I like that. And then you cache it. Okay, that's what's going on there. I like that. Much like the worm cache stuff. Yeah, you have some weird handlers because you're trying to see if it's cached rather than just running the thing. All right. Now let's go to the knock bytecode interpreter because we keep calling out to U3N. All right. U3N slam on is one of these that we need to see, and U3N knock on. All right. So U3N slam on, this is the calling convention for gates. And what we do is we receive a gate as a noun and a gate as a sample. And then we run this is tracer stuff and ref count stuff that we're passing around. I don't know why we're doing a double.
No, so actually, no, that's getting the tail.
Oh, U3T
the
is one of
tail.
these stupid
Yeah. It's
Oh,
getting the
U3,
tail,
okay,
the tail,
yeah,
and the
okay.
head of the gate. Yeah.
Okay, it's a shorthand. Okay.
Yes, and then the K increases the ref count. The Z decreases it. like
Yeah,
in
K,
signal processing.
K is bumping it.
Yeah,
Okay.
K increases it.
Okay, so explicitly we're getting the battery
Mm-hmm.
and incrementing the ref count. Then we're getting the sample,
Mm-hmm.
incrementing the ref count. This is probably some
Making
kind
a
of
cell.
tail of the tail. This is the context.
Yes.
Okay, yeah. So, okay, we're making a cell of our sample in our context. Then we're running the actual.
Yeah, you're
we're
making
making a
cell of
cell
your.
of that.
Yeah.
And then we're running kick on, but ultimately this all ends up at U3 and noun on, which is where I want to jump next. Or knock on. All right. So this is our evaluate our case here, which is basically we receive a subject and a formula. I don't know why a subject is called a bus here. Knock O. Yeah, I mean, yeah, sub is, yeah, so Trent says sub is close to subtract and bus is backwards. That's true. This is kind of an odd one though. Like, I mean, honestly, people like I don't know. There's an obsession with pronounceables in this. I'm okay with unpronounceables if they're terse and obvious, but anyway, it's fine. Who am I to do this? All right. Then we actually, okay, then we're gonna end up running a helper function. Anything that's prefixed with a cab is a helper function that's intended only for use in the file that you're currently in. And I think the things that I'm actually wondering, yeah, these things don't even get prototyped, which makes sense because you don't want anyone to use them anywhere. All right, here's where we're heading. We're heading towards the bytecode interpreter. All right, so we can burn on and burn out and blah blah blah, but where we're ultimately ending up is bytecode, which is like what we're actually going to run these things. Burn on, burn out. We want burn. Cab in, cab burn, which is defined here. Okay. All right. Go way back to maybe the first time when we were, I think the first lesson we were talking about raw hints. And one of the raw hints I demonstrated was X-ray. All right, and so X-ray lets you, define a value and then give, so here I'm making a cell against adding a value to a subject, making a cell of the value and the increment of the value. All right, so what does this actually look like in Knock bytecode? All right, so bytecode is what is actually run. This is the end result of the runtime attempting to parse noun into something. And, in principle, you should be able to build bytecode that's more efficient than Knock, and subject knowledge analysis and everything gets into this question of like, how do you build and evaluate something that's more efficient than Knock itself on a contemporary processor? So here, this Hoon code comes down to there's a literal byte 2, pushing it on the head, putting these things together. I think bump is our increment. And then anyway, so you end up all the way down at halt and you've completed evaluating this statement. All right. We don't need to do a lot in the bytecode unless this becomes your purview in Urbit Core Dev. But it is a thing that gets built, and then what U3N is ultimately running in cab end cab burn is knock bytecode. So it gets the opcode table. We'll take a look at the opcode table in just a minute. And then it's just going to have a big switch processor that matches each one of these and then processes it down into everything that's going on. So if I actually want to see, there's my little literal byte. Like what we're doing are stack ops in evaluating these. So let me see what a do alt looks like, for instance. Okay, so that's a lose. That's like, we don't need this value anymore. What's a do bump? My guess was yeah, so this is an increment because U3 int is to increment a single atom and not lose it. All right. Yeah, so you can process these, but like I say, unless you end up like actually needing to write and evaluate these, you won't need to know more about this other than the fact that it exists. Now, one of the interesting things about knock bytecode is it uses this thing called the X macro. And it actually, yeah, okay, it even calls it out here in the docs here. But the X macro allows us to do a pound define that is basically tabular in format. So we can define all these references to everything and then process them more efficiently, like write our code more efficiently. And yet these are still preprocessor directives that we've produced here. This is one of these bits of C deep lore that's in there. This is probably, the knock bytecode is essentially undocumented. This is like the closest to documentation that exists for it, is that we have outline statements to each of these things that's being processed here. And then, of course, how they relate to knock itself. Right, Moffel points out it was written by one person working on it part-time. And it's like, it's fine, right? Like, it's actually been good enough for a really long time for what it needs to be, but it's also a thing that has never been optimized before the Aries work. The Vere implementation has never really been optimized. So it's here, it's kind of neat. There's lots of studies that could be made, right? Like we have literal 0 and literal 1 hard coded here. Does it make sense to do other things in your bytecode? Other literals are common enough to matter. Like, who knows, right? You'd have to go, like, actually, I guess, write code, write knock and write bytecode and do some good statistical comparisons to figure out what's going on there and benchmark that. All right. So yeah, so one of the objectives of Aries is to improve on bytecode, but this is what it looks like and where it gets run. All right, there's U3Js, the Jet dashboard stuff. We kind of talked about that before. Yeah, so it deals with the state. So the Jet dashboard, the purpose that it's trying to resolve is not only Jet dispatch, but historical Jet dispatch, right? So the Jet dashboard registers, validates, and runs Jets. And it also has to do a little bit of security protection, because you don't know, all right? So like the naive way of implementing a Jet would be register a Jet, and then your runtime goes and runs whatever this Jet is, right? It just looks in a table, finds it, and looks it up. This would actually be a huge security problem, because if you ever had your Vere compromised, like, who knows what you're running, right? Like those Jets could do anything. The Jet dashboard maintains like your breadcrumbs of Jet registration and so forth in a way that's supposed to help with that, is intended to do so. So it keeps track of the Jets that are currently operational on your runtime. It keeps track of the Jets that were actually run in the history of your log. So if you do an event log replay, you have that information about the jets that were run. It'll still do like a regular replay. If a jet's not available, then it'll run the knock and so forth. And then it maintains what's called warm state, which are the dependencies between what you actually have in your current runtime and then what was run historically in your system. Kind of complicated, but that's all it's instrumenting for you as you run this. Now, what I think is far more interesting, and for most of you probably the place that, unless you get into writing veins, this is probably the place you're likely to get deeper into the runtime first, is jets. So let's take a look at a few jets and see how these things are set up. All right, so let's look at, in jets B, let's look at length. All right, so we remember what length does. Given a list, it returns the value of the list. So let's look at what everything in this file. This file's 37 lines long with some blanks. All right, the entry point for your jet is always the W file. This is what's going to be registered in tree.c. This is what the jet dashboard is going to point everyone towards. The goal of your W file is to unpack your values from your sample. So U3X extract, crash on failure. If you give it the wrong shape of sample, it's going to crash. U3X SAM is an address shorthand. These are, let's see, I think these are in extract.h. Yeah. So here you have all these hard-coded addresses just as shorthand for what's going on. Most of the time you don't need to get outside of these. Actually, when I was writing the original version of Lagoon and doing the jets for that, I actually ended up with a function that had like 6 or 7 arguments, and I actually like went past the sample for this, and I had to go back in here and figure out what was going on with this for the first time in my life, how it was generating these values, because I was running out the sample. All right, back to length. All right, so this is going to extract and validate your values, and typically it'll have a crash here if things don't work. And it can be different kinds of crashes. There's U3M bails and so forth that gets generated. It often does a check to make sure that it's an atom or a cell or whatever. In this case, it doesn't do that check here. And then it calls one of the others, the Q or the B. All right. These are the difference in your transfer and your retain semantics. Your Q is your transfer semantics. Your K is your retain semantics. So your K also calls your Q, but then manually frees its value when it's done because it knows that it's not needed anymore. And it received the value was brought to it, and then it frees it after it's done. All right, back up here, what is actually happening? We're defining a length. How are we actually measuring the length?
Onto the tail. So it's
We're just popping the tail. We're just taking the tail every time, incrementing our length.
like a linked list C
Yep.
implementation, basically.
Right. And it is, right, it is a linked list because your noun only, right, if you go back to that struct, it knows nothing about the actual layout. So you actually don't have a different way of doing this. You do just have to iterate all the way through your linked list. I mean, the other thing you could do is, I guess you could store some metadata with it. But, that would introduce a little bit more cumbersome work. And then we do U3I word, we could also have done words. 1 comma would have been the same operation. All right, that's length. The algorithm looks pretty much the same as it does in Hoon for similar reasons. Let's look at turn. All right. So turn does not have a K version. It only has a W and a Q. That's more common to only have a W and a Q. So it extracts the sample at 2 and the sample 3, those values. So I guess 12 and 13. And then it runs turn. And so what's actually happening in turn is you sort of warm up this gate in the jet dashboard. Then you extract your cell value into T. Right, so you're getting T as the tail of those things that you had, doing this constructor stuff and slamming a gate on the value that you just pulled off, and then going until you hit that U3 null again. Also reminding you that U3 none is different than U3 null. So yeah, this is also pretty similar to the Hoon implementation. They're not all. Sometimes they're quite different. Let's go to another one I thought would be interesting was Peg. Yeah, so Peg is a good one because Peg is very different from the Hoon. So do you want to have let me see if I have Hoon.Hoon handy. Yeah, I do. Okay. Let me find the Hoon version of this. All right, so what Peg does, Peg gives you the relative value. It gives you the absolute value of the relative value within a tree address. All right, so, in a sense, like, that's pretty straightforward. There's actually several different ways you can calculate this. The Hoon does it this way. I guess let me. All right, so Hoon does it this way, where it switches on B, and if B is 1, it returns A. If it's 2, it returns mole A2. If it's 3, it returns the increment of mole A2. And if it's something else, then it recurses on itself and does the calculation again. All right, so if it's not a direct child of the tree, recurse into the tree and keep finding this value. Pretty straightforward. The C actually tries to do some clever stuff about what's the length of my tree, and then sort of like relatively situate myself in my tree with these decrements and these left shifts, and then add these values together, and then it has all these frees, and then it returns this final value out. Right, like it actually ends up looking really different, and it ends up calling several other jets. It's probably not that efficient because every one of those jet calls is also going to have to unpack the atom and then package it back up and then return this value back to you. The Aries jet looks even more different. The Aries jet just takes advantage of the fact that that it's a 0 or a 1, a head or a tail, and you can do this clever arithmetic by just appending the two values together and treating them as an integer, and it's incredibly fast. Right, so the two runtimes actually have different implementations of this jet, which is great, right? Like we're triangulating on. There's not one right way to do it. There's one right answer, but there's not one right way to do it. Peg's not called often enough that this being inefficient is a big deal, but you can be clever. Let's see. Let's look at my favorite. All right, I love floating point because I understand it. All right, this is single precision floating point. This is RS. So if we want to add two values together as dot 1, dot 2, we use the RS core for it and get the value out. So what's actually happening here? We have a W. All right, U3W. I don't know what ET is for, but E is where we are, which makes sense. I don't know what the T is from, though. Interesting. All right, this one is kind of I would consider this to be a more conventional unpacking than the ones I showed you before. So this one actually has a number of checks and then an explicit bail if something goes wrong. So it extracts 2 and 3. It verifies that this is an atom. Because this is an if any of these are true, then fail. Rather than the opposite logic. Make sure these are atoms, and then if they're not atoms, it crashes, and then it goes ahead and it calls. Okay, what's this bit? I'm receiving a core. What's U3X at 30?
Is that just addressing it? I don't know what's at Axis 30, but that would be my guess.
It's grabbing something at a certain address. So what does R look like? So when we run R, we are actually running a door. RS is actually a door with a sample that affects the rounding mode, the floating point rounding mode in IEEE 754 floating point logic. So we are grabbing the door sample, which is one of the inputs to doing addition correctly. So getting 30 out of our noun retrieves the door sample from our context. Then this comes up here and we get an A and a B and then an R, which is our rounding mode. So we have to set a rounding mode, which is this utility function that sets, we're actually doing software floating point. We're not doing hardware floating point. So we have to do weird things to add the two values together. And since we might be working with not a numbers, the Vere runtime runs nan unify, which if it is a nan, if it's not a number, it is this not a number, rather than just a generic. There's a whole field of floating point values that are not a number. But we have this not a number that we're running into in this particular case. Rounding mode only matters when you're doing certain really complicated operations. Let me see if I can find one here. Maybe like a div might run into this. Let's try. Yeah, so if I change to round up, I get 3666667. If I change to round down or round towards 0, I get a different value in my least significant bit. And then there's also N, which is, I don't remember what N stands for. Actually, I think it tells me here. Round near, even, round towards 0, round up, round down. Okay, yeah. All right, and then you had to unwrap the value, and you have to wrap the value back up on the other side. All right, one more I wanted to look at, which is SLA. All right, so what does SLA do? There we go. All right, so it returns a unitized parsing of a value. So this is actually kind of a complicated function because you have to be able to parse whatever thing you're getting, and then like turn it into a Hoon piece. SLA is rather complicated. So first off, it extracts your sample. Then it checks, is it DA? Is it a P? Is it a UD? Or is it a TAS? And in those cases, it has helper functions to hit each one of those. Otherwise, it returns U3 none, which tells Vere to just run the knock instead. So now if you're running to parse a P, you actually are trying to, there's these are all macros. This is such a weird function. You're trying to process one of these values forward So then check, is this a valid suffix syllable? If it is, we keep going. And then you keep parsing these forward one at a time to make this happen. Yeah, then there's anyway, you end up having to deal with everything all the way down to comments to make these happen, right? So if you hit the last comment, then you have to hit all of these, ensure not end, and so forth. If you're too long, you're not a pat P. You could be a pat Q, right? But pat Q is going to get processed in whom. Then it alternates prefix and suffix lookups all the way down and returns the combination of all of these. Kind of an interesting mess. I do want to show you what the macros for these are like, because it's doing this whole like, can I get a value and return something out of it from processing that one thing, right? But what's also interesting is that as a macro, it is introducing a variable. Right, try get syllable is introducing a variable into your namespace. This is weird code. Yeah, and it's naming it dynamically. There's some, like, honestly, this is like the kind of code that I would not have like naively expected to be able to write in C. Like dynamically introduce variable names into your scope like this. And then the syllable stuff is I'm trying to remember where these are defined. I know they've got a huge table of them somewhere, although they may actually be defined as motes. I don't know. Anyway, they're in there somewhere. It doesn't matter. Okay. So those are some of the things there. All right, we're just about done. I'm not going to talk about snapshotting today because I'm going to bundle all the memory stuff next week. I think what we're going to have you do for homework this time is write a short program using U3 that actually has to deal with ref counting, like pass a value between several things, and then do it all without memory leaking. Ted and I discussed this and came up with an idea for it, but I need to actually spec it out in sufficient detail as a homework. So it might be a day or two till I get a chance to write that up in a proper format for you. But it'll basically be, how do I use C3 and U3 correctly in Vere? Like what does that look like? So it might be like a toy jet, but then the actual C code has to do some fancy things just to demonstrate what's going on. Because I'm not sure naively how straightforward it is to just link against U3 if you're not also trying to build Vere.
It's not.
Okay.
It's a pain.
Yeah, I figure there's probably dependencies in there that are implicit.
Yeah.
So
related to that, is it easy to do like a memory check on all of Vere? Like you just
No.
run Valgrind on it, and does it like?
No.
It's not.
Not at all.
Okay.
I
is-
will talk about how to hook Valgrind up next time.
But
Okay.
Valgrind, can you do it on the loom?
You can.
Really? Joe hasn't told me how to do that yet.
Yeah, it doesn't work great. So I'm sort of like, I'm going to tell you this because it can be done, not because I have found it terribly useful myself. But I'm going to talk about GDB and Valgrind and stuff in the runtime next time. You have to do some tricks with, basically you have to change some hard-coded values on memory space allocation in Vere. You might be able to do this with the command line flags and get it small enough, but Valgrind takes up like 4 to 6 times as much memory as what it's instrumenting.
Mm-hmm.
And so to even get it to run with Vere, you have to like dramatically shrink the space that Vere and Arvo are allowed to use.
Usually, I thought you had to use it on a custom allocator, and it's just a pain. Is that what you have to do? Just set it up to use it on the allocator?
Well, it's not loom aware in that everything boils back down to it's a C malloc,
Okay.
right? Like it doesn't know about U3A malloc,
Okay.
but it will tell you about like global memory leaks. Right. It won't
Okay.
tell you, oh, you're doing something bad on the loom because it doesn't know about the loom.
No, so it's not really useful. Well,
It's useful if you're debugging Vere instead of like Arvo running on Vere.
I don't know.
Yeah, I guess that's a good point. It's like you're
It's not. I don't know.
you're trying to debug your own like memory allocation system, which like on the whole may not actually be leaking memory relative to like the operating system, like the base operating system, but it may be internally. Yeah, I don't know really how you. I'd be curious to know what the debugging tools are for that, if any, in the Vere space. Go ahead.
And I have not done it since the guard page stuff came online.
Okay.
So we may just experiment next time. And like, I know I've done it. I've hooked it up because there was a memory leak a couple of years ago. I was really trying to track down, which I never tracked down because I think it was not, I think where I was working was triggering it, but it was not the source of it. And then later on, we tried the same thing again and it didn't have the memory leak problem. So we cleaned up a memory leak somewhere that was just a latent bug that we never identified.